Hello everyone and welcome to this lecture. In this lectures and subsequent lectures, we will be talking about expanders and Ramanujan graphs. One of the most beautiful class of graphs, one of the most useful class of graphs. Okay, and by the way, I will be making use of slides here because the topics are slightly advanced. So I will be actually not proving many things here. Sometime I will be proving, that time I will be making use of writing pad. Otherwise, I will be using slides here. Okay, so and as I mentioned that there are many uses of expanders and Ramanujan graphs. So I have listed down few uses. As soon as we will know the definition of expanders and Ramanujan graphs, some of the uses are actually apparent, very obvious, right? But some are actually very counterintuitive. It is kind of surprising that Ramanujan graphs and expanders are used in actually quantum cryptography, sorting networks, and many more. Okay, error correction codes. Okay. So what are expanders? So let us start the journey with expanders. Okay, expanders are very loosely speaking, these are the graphs which have very few edges. Okay, so we call them sparse graphs, but they are well connected. Well connected means even if something is destroyed, some vertices, some edges are removed from the graph, the graph is still maybe you can say connected, right? It's very hard to disconnect this graph. Then we call that this graph is well connected. Okay, but again these two things are subjective, right? Sparse, as I said that there are very few uses. Maybe the very few for you may not be very few for me. Okay, so let us now go ahead with slightly more formal terminologies for these two quantities. And by the way, it appears that these two quantities are counterintuitive. Competitive one. On one hand we are saying that there will be very few edges, on the other hand we are saying it should be very well connected, but after removing the edges or vertices, the graphs is still connected, at least connected. Okay, so it appears that these are competitive. These both properties are competitive. Okay, so let us see what sparse for us will be. Okay, so if there are n vertices in the graph, how many edges the graph could have? Okay, there could be NC2 edges, right? Okay, and by the way, in the study of expanders and Ramanujan graphs, we will be taking the graphs which have multi-edges and self-loops also. But yes, overall these graphs are sparse, okay, and well connected. So let us focus on the sparsity here. Sparse for us will be some graphs which have linear order of edges rather than quadratic. Remember, NC2 or close to NC2 is quadratic, right? Order of n square, right? But we want something where the edges are linear order in terms of n. Okay, and very typical kind of graphs are what? D regular graphs, where the degree is some constant number. Okay, so where D is some constant. So what are the edges in regular graphs? So if it's a D regular graph, what are the edges? It's a D into n by 2, where D is constant, so it's order of n. As n is increasing, D is fixed, the number of edges grow linearly rather than quadratically. So we will be actually focusing on most of the time on D regular case. Okay, very good. Yeah. Now, for example, this graph here. So every vertex has three regular graph. Okay, so number of edges is just 3n by 2. Okay, very good. So let us now go ahead with well connected. Again, just look at the picture here. Okay, a very informal kind of notion I will give you what well connectedness here means. If you see here, I have on the left hand side, I have trimmed out some subset, okay, which is shown in green color, maybe it's a green color, okay. So if you see that the number of edges which are going from green to white or green to its complement, so how many edges are there? 1, 2, 3, 4, 5, 6, 7. So set of these edges are called boundary of that green. They are basically boundary of that subset. Okay, now well connectedness means every subset has a very good boundary. Okay, so for example, in the right hand side, if you see, suppose I pick the vertices which are in gray region, okay, it has a very good boundary with its complement. If you see that, how many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 edges in the boundary. it means if the boundary is very good, if the boundary is large, that means in order to remove that subset from the rest of the graph, you need to kill many edges. If the boundary is large, that means you have to kill large number of edges, right? So basically every subset of vertices has a large boundary. This is the notion of well connectedness. We will now solve the say it more formally, okay, by in terms of giving some number, that beautiful number we call Cheeger's number, Cheeger's constant, isoperimetric number, expansion ratio, and so on. Many names given to that number, or that will determine basically that number determines how well connected a graph is. Okay, so very good. By the way, our brain graph, okay, is a very good expander. Okay, so in our brain graph, how many neurons are there? Number of neurons are roughly 10 raised to the power 11, but every neuron is only connected to 7,000 other neurons on an average. Okay, so very less fraction of the total number of neurons a neuron is connected with. So it's a very sparse graph, but you see we all functions very well, right? So our brain function very well. So this is a very well connected graph and sparse also. Now let us go to the a criteria or a number which will actually quantize what we mean by well connectedness. Okay, so this is something called expansion ratio, very famous term, very famous number. Okay, so expansion ratio of a graph is, you look at this basically a ratio. So on the numerator side there is something called ds. So S here is some subset, ds tells the boundary of that subset, and we are taking the number of edges in that boundary, so mod of this divided by the number of vertices in that subset, and you do this for all possible subsets. Okay, and ideally you take subsets of size less or equal to n by 2, because if you pick a subset and its complement, one of them has to be size less or equal to n by 2. So we are taking basically all the subset which have size less or equal to number of vertices by 2. Okay, so and we take minimum of that ratio over all possible subsets. Okay, and this we call, ideally we call it edge expansion ratio. Now there is something called vertex expansion ratio. In the vertex expansion ratio, this ds, remember ds is what? ds is the boundary of subset S, the number of edges which are going from S to its complement. Okay, in vertex expansion ratio we replace ds by the number of vertices such that these vertices have at least one neighbor in S. Okay, so and the rest of the definition is same. Okay, and by the way, this vertex expansion ratio and edge expansion ratio for D regular graphs, we mostly will be dealing with D regular graph. These are equivalent. So we will be focusing on this edge expansion ratio. Basically by means of expansion ratio we will mean that edge expansion ratio. Okay, and this ratio is also known as isoperimetric number or Cheeger's constant. Okay, now let us go ahead, and one implication of this expansion ratio, which we denote by hg, is that if you pick any subset S, okay, and suppose the expansion ratio of graph is hg, that means the boundary will be at least hg into the minimum of the size of S or its complement. Okay, so basically this. Very good. Yeah, great. But we will see that, meanwhile you keep on thinking how to calculate hg. Okay, is it easy to calculate hg for a given graph? Okay, even just focus on just D regular graph. Is it easy to find what hg will be? Okay, so let us go ahead. Okay, and let us take some example. What will be h of basically the expansion ratio of cyclic graph, or not cyclic graph but cycle graph, a cycle on n vertex? What will be its hg? What will be its expansion ratio? Okay, so cycle graph is, suppose if I draw it something like this, suppose this on 6 vertices, hg you can actually calculate. So it's a minimum overall possible, right? ds divided by S, right? So you can actually take half of the vertices here and rest of the half vertices are different, its complement, and ds will be what? So number of edges which are going for, suppose this is S, right? So how many edges are going from S to its complement? There are only 2 edges. There are only, so it's a 2 divided by n by 2, right? So it's actually 4 by n. And if you see that when n grows big, the expansion ratio goes very, very down. In fact, when n tends to infinity, the expansion ratio goes to 0. Okay, very good. What about the complete graphs? What about the complete graph? Complete graph, if you see that every vertex is connected to every other, has edge to every other vertex, right? So, okay, so maybe this is a complete graph. Yeah, this one. Right. Again, I mean, we have to find the minimum ratio, right? ds by s. So you can again take half of the vertices. You assume that n is even in both of the case. Otherwise, I mean, just maybe plus or minus one thing will be there. So roughly n by 2 again. Okay. So n by 2. So how many edges in the boundary of any subset which of size n by 2? There will be n by 2 edges because there are rest of the vertices are n by 2. Okay. And divided by what? Oh, sorry, n by 2 times n by 2 here. Okay, because there are n by 2 vertices in S, and all of these vertices are having edge with all the rest of the vertices. And what is the size of the set is n by 2, so the expansion ratio comes here n by 2. You see that when n goes infinity, the expansion ratio also goes infinity. Okay, and now these are some very, very easy to see. The Peterson graph has expansion ratio 1 if you just focus on this subset. Okay, so expansion ratio is coming out to be 1. Okay, and for all the connected graphs, Hg will be always positive. Why it is so? Why it is so? See, if it is a disconnected, you pick a disconnected component, its boundary is what? Its bound, all the vertices, all the vertices in a component will have boundary 0 because it does not have any edge with one other component. Okay, so boundary will be 0, hence the Hg in that case will be 0 if the graph is disconnected. Okay, very good. Now comes the very, very important definition. Till now I have made use of expanders. Actually, when we say expanders, we talk about the family of expanders. Okay, and this is a growing family. Basically, let me actually state it: a family of graphs G1, G2, G3 and up to G infinity, where these guys are these Gi's are increasing order in terms of number of vertices. Okay, but with one property, in fact two properties. All of these graphs are firstly d-regular graph with fixed degree. Okay, and another thing is the expansion coefficient of all these graphs or every member is positive. Okay, by this immediate by the definition, the immediate consequence is the family of cyclic graph is not expander. Why? It is not an expander family or expander graph. Why? Because as n is growing, right, the expansion ratio goes to 0, and in the when n is actually infinity, the expansion ratio is 0, right? Okay, and what about the complete graph? Okay, you may see that expansion ratio is I mean, when n is growing, right, n is suppose tending to infinity, the expansion ratio is very high. It is also going to infinity, but still it is not a family of expander. Why it is so? It is so due to the definition. We want the degree to be fixed, right? When n is growing, in case of complete graph, the degree is also growing. Degree is n minus 1, so it is also growing with n. We want degree to be fixed. So, cyclic graphs and complete graphs are not the family of expander graphs. Then can you give me one family of expander graphs? By the way, as I mentioned earlier, right, we want the sparsity, basically d-regular case where d is fixed. Okay, but we want Hg to be always positive for every member, right, and is increasing. Okay, earlier it was used to believe that such family does not exist. Basically, it was too much to ask for. Oh, on one hand we are saying the graph has to be very, very sparse, okay, and also very well connected. There will be a time when we are increasing n, the graph will become disconnected. Okay, earlier this was the notion, but then mathematicians, they come up with Very nice construction of this. We will see this construction maybe in the next lecture. Okay, the first explicit construction came in 1973 by Margulis. Okay, we will see this in next lecture. Okay. Meanwhile, you can keep on guessing, the difficulty in coming up with the family of expander graphs. In fact, the explicit expander graph where you can actually determine this vertex is connected to these many other vertices. Okay, very good. One challenge is what, as I mentioned just 5-10 minutes back, what about HG? Okay, how to compute HG? Well, the definition says that the HG of every member must be positive, but how to compute? Even if you try to give the family of such graphs, but we have to actually make sure that HG is positive. Okay. Unfortunately, there is no polynomial time algorithm for it. There is no polynomial time algorithm for it. Okay, it is, again, if you come up with a polynomial time algorithm, so it's actually one of the 7 millennium problem of the world at present. If you can come up with one polynomial time algorithm for it, the famous conjecture in the theoretical computer science, P versus NP will be settled, then P will be equal to NP. Very good. Okay, so now let us move to the next stuff. Now there is a good news for us. HG is very difficult for computationally very hard problem. There is no polynomial time algorithm, but fortunately these two mathematicians Alone and Millman in 1985 gave very nice bounds on expansor ratio for D regular graph. Okay, remember, if it is D regular, the largest eigenvalue is by default D. Okay, the second largest eigenvalue, suppose we call it lambda 2. Okay, and by the way, we have also seen that the lambda n equal to minus d if and only if G is bipartite, and of course when this graph is connected, this D regular graph is connected. Otherwise, we have seen that, right? In case of bipartite graph, the eigenvalues are symmetric, but when the graph is connected, we can just by looking at the first and the last eigenvalue, we can determine whether the graph is bipartite or not. Okay, if lambda 1 equal to minus lambda n, then graph is bipartite, otherwise not, in case of when graph is connected. Very good. So these two great men actually gave a very nice bound on expansor ratio. Now this, let me read. The expansor ratio is always greater than d minus lambda 2 divided by 2, okay, and always less or equal to square root of 2d and times d minus lambda 2. We will see the proof of the lower bound in the next lecture, but if you see on both hand side, there is a quantity we call d minus lambda 2. If this quantity is more, right, then it means that HG is more and graph is more well connected. Okay, better well connected. Okay, and so this is d minus lambda, d is constant. That means what? If lambda 2 is small, d minus lambda 2 will be large, right? So we want graphs where lambda 2 is small. Okay, D regular graphs where lambda 2 is small, and this will give you, this might actually give you family of expanders. Okay, if you can generate such graphs where lambda 2 is always at least strictly lesser than D. Remember, if lambda 2 becomes D, the graph is disconnected, right? So lambda 2 has to be lesser than D, okay, for every member of that family, okay, and more lesser, better the family, better the HG will be. Okay, so we will see some of the basically construction, okay, and some of the example in the next lecture. Meanwhile, you keep on thinking about some construction of, maybe manually you try to make family of D regular graph and such that the exponential ratio of every, basically you keep on growing, keep on increase the number of vertices, still every member is connected. Okay, and by the way, this d minus lambda 2 is famously called as spectral gap. Larger will be the spectral gap, larger will be, better will be your exponential ratio, larger will be the exponential ratio, and better will be the connectivity of a graph. Okay, so with this I am stopping this lecture. In the next lecture we will be talking about a very famous lemma that we call expander mixing lemma, and also a proof on one bound on alone and Millman result about this. Okay, so till then, thank you very much and see you in the next lecture.